In Unit 1, Lesson 6, we are moving on to Chapter 7 in the textbook, moving on to dealing with rational functions and rational problems in general. It's going to be connected. We're still going to be using a lot of the same stuff we just did, but we're moving into rationals, which essentially means fractions. So you can see the two objectives. We're going to find the domain of a rational function, and we're going to simplify rational expressions. Let's get started. First of all, what is a rational function? A rational function is any function. I'll just use function notation here. Remember, f of x means the same thing as y. That's just function notation for y. That is equal to p over q, and I'm using capital P and capital Q here just as letters, where p and q represent polynomials. And another important characteristic, q is not equal to 0. Right? Because we can't have 0 on the bottom of a fraction, can we? No, we cannot. So what are we saying? We're saying a rational function is just a function where you take two polynomials and you put them in a fraction, essentially. Now, the polynomial on the bottom, to be clear here, the q, polynomial doesn't automatically mean there's variables in it. It could be a single term polynomial, which of course we call a monomial, and that q could just be a number. So there's no guarantee that there's a fraction, or I'm sorry, a variable on the bottom of the fraction. But what we're interested in is the domain of these functions. So let's just look at an example. Let's say we have f of x equals 8x cubed plus 7x squared plus 20, all of that over 2. Now, this qualifies as a rational function. We would say this top part is p, and this bottom part, in this case just a 2, is q. Now, we don't have to, the p and q are just letters. They don't mean anything. They're just placeholders, so don't get stuck on me using those letters. But the point is we have a fraction and we've got polynomials, so this is a rational function. Now, what is the domain? Hopefully you've heard that term before, and you'll recall that the domain for any function in general, the domain is the set of all x values. Okay. And I'll say all x values included in the function. Because there could be some x values that are not included, and that's what we're trying to figure out. So when we look at this function, you're thinking, well, is there any number that if I plugged it in for x, like if I said, what is f of 12? If I replaced x with 12, well, what would that mean? That would mean coming over here and saying 8 times 12 to the third power plus 7 times 12 squared plus 20, all of that divided by 2, because I would just replace x with 12 everywhere I see an x. Okay, well, 12 is just one example. Is there any number that if I replace x with that number, I will not get an answer for f of x? In other words, as I look at, and I really put these too close together so it's hard to separate, but as I look at this function, is there any number I cannot plug in for x that I would not get an answer back for? And the answer is no. No matter what number you plug in for x here, you'll always get a solution for f of x. There's two things you want to look for, and this will really narrow it down for you. When we're thinking about domain, there's two possible restrictions on the domain. The two things that affect domain, and I'm going to just write these out because I want to be perfectly clear here. Alright, let's think about if you had a square root. If you have a square root function, you can't have a negative number under a square root, and get a real number answer anyway. All right, so anytime you have, or any even root for that matter, it could be a fourth root or a sixth root, if you have a function that has a square root in it, then your domain could be restricted if there's any values of x that would make the part under the square root be negative. We don't have that here. We're not going to be dealing with any square roots in this unit, so you can forget about that one. That was the first one. The second one is, and this is the one we're dealing with right now, the denominator. If you have a fraction, the denominator cannot equal 0. Of course, you know that symbol, the equal sign with the slash through it, means not equal to. So what you really should be looking for here on restrictions for the domain is, are there any values of x that would make the denominator 0? If so, those cannot be in the domain, because that would leave me with an undefined function. Now, for this function we just looked at, there's not, because, you know, what is our denominator? Well, our denominator is just 2. No matter what you plug in for x, that's always going to be 2. So you're always going to be able to divide by 2. That will always give me an answer. Let's look at an example of one that is not. Well, actually, first let me say this. Let me give you a bunch of different ways to say this, because you may be asked to write it multiple ways. We would say, then, for this, the solution, the domain, you might have a capital D like that for domain, is all real numbers. Okay? All real numbers, that's one way to say this, because there was no restriction on the domain. And by the way, if you ever see this symbol, it's an R with 2 vertical lines instead of 1, that is the symbol for all real numbers. All right, so I'll just put an equal sign here. That's the symbol for all real numbers. All right. Another way to say this, you could say it in interval notation. You could say all values from negative infinity to positive infinity. Well, that's everything. That's interval notation for that. You could write it as an inequality. You could say negative infinity is less than x is less than infinity. And then you could also use set builder notation, and you will see this in my math lab some. And it'll look like this. There's an x and then a vertical bar and then something you have to fill in. Well, in this case, how you read this is x, all x such that. This vertical bar means such that. All x such that. And now we can just write however we want. We want x is a real number, is one way to say this. But you'll see this more often when you don't have all real numbers. And I'm about to show you one that doesn't. So let's look at a different function. Say g of x, and I'm just using g for variety here. G of x instead of f of x really doesn't matter. 5x squared minus 3 over x minus 1. Now first we should look and see, can we reduce this anyway? Is there any way to simplify this? And there's not, because there's nothing on the top or the bottom that can be factored. Okay? But if I'm concerned with the domain, well, now I do have an x in the denominator. All I want to do is look at the denominator. So I look down here and I see, well, I've got x minus 1 in the denominator. So what value of x would make the denominator 0? So all you have to do is take that denominator, set it equal to 0. As you can see, we would have to add 1 to both sides, and we get x is equal to 1. So what happens to this function if I plug in 1? Well, let's see. G of 1 is equal to 5 times 1 squared minus 3 over 1 minus 1. What does this give me? Well, this gives me 2 on top and 0 on the bottom. And what is 2 divided by 0? Remember, that is undefined. We cannot divide anything by 0. I'll put some exclamation points on it to make sure we know it's important. So we have a 0 on the bottom of the fraction. It's undefined. That tells me x equals 1 is not in the domain. So x cannot be 1. So in this case, when we go to answer the question and we say, what is the domain? We might say all x such that x is not equal to 1. And that's saying x can be anything else other than 1, but it can't be 1, and that's my domain. That would be your domain in set builder notation. In interval notation, we would say anything from negative infinity to 1, not including 1, so we put a parenthesis there. Union, we use this union symbol to mean or this other interval over here, anything from 1 to positive infinity. So what is this saying? It's essentially saying it's saying the exact same thing in a different way. X can be anything over here between negative infinity and positive 1, or it can be anything between 1 and positive infinity. It just can't be 1. It's just another way to say the same thing. All right, let's look at one more of these, and then we'll move on to simplifying these expressions. Let me give you one that requires slightly more effort. All right, again, all I'm concerned with, if I'm looking at the domain, all I'm concerned with is that denominator. All that matters is what values of x would make the denominator equal 0. And by the way, just because there's an x in the denominator doesn't automatically mean that there will be some values that will make it equal 0. For instance, over here on the side, let me give you this. In this function, think about x squared plus 1. No matter what I plug in for x, it's going to be either 0 or a positive number. So when I take that value and I add 1 to it, in this case, this denominator can never equal 0. So just because there's an x in the denominator does not automatically guarantee that you're going to have some values that are excluded from the domain. We still need to check and make sure. Well, in this case, our denominator, back to this original problem, h of x, this denominator can be factored. In fact, it's one you've seen factored before in other lessons. It's one we've used quite a bit. X and x. Notice that I have a negative 15, so that's a plus and a minus. And what multiplies to make 15, but when I subtract I get negative 2. That would be a positive 3 and a negative 5. Okay, well, I have now factored the denominator, and if you'll recall from the previous lesson, if we're setting this equal to 0, it means we have two factors that could equal 0. So we take x plus 3 and set it equal to 0. We also take x minus 5 and set it equal to 0. And this gives me x equals negative 3 and x equals positive 5. So what are we saying? We're saying if x is either of these two numbers, negative 3 or positive 5, we're going to have 0 in the denominator, which makes the function undefined. Therefore, our domain is... Wow, what happened to my bird there? My bird got punched in the head. It got a little wonky. My brackets, I need to fix that. All x such that x is not equal to negative 3 or 5. And that's the most likely way that you would enter this in my math lab. So they'll probably use set builder notation. X can be anything else, but those two values give me a 0 in the denominator, so can't have it. All right, let's move on to our next objective, which was to simplify these expressions. Now, if we've got polynomials on the top and on the bottom, and we know that we can factor polynomials in lots of cases, then it's possible that we have some things that will cancel out. All right, looking at this polynomial, okay, I'm sorry, this rational expression. On top, we just have a single term, 2x squared. There's nothing we can do with that right now. But if you look at the denominator, both of these, we've got a 10 and a 2. Those are both divisible by 2. And then we have x cubed and x squared. Well, those both have at least an x squared in them, so they're both divisible by x squared. So I can factor that out. I've got 2x squared on top, and I'm actually going to factor a 2x squared out of the denominator, leaving me with, well, if I take 10x cubed and divide by 2x squared, I'm left with 5x. 10 divided by 2 is 5, and x cubed divided by x squared, there's only a single x left. And then if I take 2x squared and divide it by 2x squared, well, I factored that entire term out. It cancels itself out, and all that's left is a 1. So now, having factored the denominator, I see that I now have something I can cancel on top and bottom. I've got 2x squared over 2x squared. Well, those are both going to go to 1. They're both going to become 1 because they can cancel each other out. Remember, anything divided by itself is 1. So now what am I left with? Well, the entire numerator becomes 1. It all got canceled. And all that's left on the denominator is 5x minus 1. And there is the simplified version of the original radical expression. All right, let's do one that's more complex, because I know you like to be challenged a little bit. Nine x squared plus 13x plus 4 over 8x squared plus x minus 7. Oh no, what's he making us do now? Well, we have trinomials on top and bottom, and neither of them has a greatest common factor. Neither has a GCF that I can factor out. And notice that both have a leading coefficient that is not 1. Well, that tells us then that we're going to have to factor by grouping. Oh no. However, it's not going to be that bad. All right, let's look at the top first. Let's ignore the bottom for a second. Let's just look at the top. Remember our process for doing factor by grouping. We do A times C. So in this case, A, let me just write it out over here. A is equal to 9. C is equal to 4. So A times C is 36. Now what we want to do is find numbers that multiply to make 36, but that add to make this middle term 13, because we still need that to be 13x. That's the one we're going to split up. Well, conveniently, they're actually listed for you already. They're right here. 9 times 4. 9 times 4 is 36. 9 plus 4 is 13. We don't even have to go looking through all of the factors. We found it already. But remember, if you didn't see that right away, list out the factors. You've got 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. There's all of the possibilities. We know that our answer has to come from one of those 5. And of course it does. It's the 4 and the 9. So, if I split up the top, then I've got, I'll just have to, let me just come down a little bit. I have 9x squared plus, now here comes the split. I'm taking that 13x and I'm splitting it into 9x plus 4x. And then plus 4 is still on the end. Alright, now let's do the same thing with the bottom. You can see that we're going to be able to factor by grouping the top here, which we'll get to in just a second. But let's do the same thing with the denominator. A times C. Well, on the denominator, I'm going to get rid of these other factors over here because they're in my way. Do this in a different color. On the denominator, we've got A times C is 8 times a negative 7, because C is a negative 7, which of course is negative 56. Alright, so we need numbers that multiply to negative 56, but when we add them, what do we get? When we add them, we get positive 1. Keep in mind, there's an understood 1 here. Right? That's 1x. Even though we just wrote it as x, it's understood to be 1x. Well, again, you could go list the factors of 56, but the answer is right in front of you. 8 and negative 7. That is the solution. But again, I encourage you, if you didn't see that right away, list out all of the possible combinations that give you 56. Yeah, it might take you a minute, but it'll get you to the right place. So now in the denominator I have 8x squared plus 8x minus 7x. Remember, one's a plus and one's a minus down here because we've got a negative 56 that we're multiplying to, and we're subtracting them to get positive 1, and then minus 7. Right, now we are set up to group and factor on top and on bottom. So let me just come sideways with this. Let's put the parentheses in here. We know we're putting parentheses there and there. We're going to put parentheses here and here I'm going to change this to plus a negative and be able to put that in the parentheses like that. So now what do we have? Well, in the first pair on top, 9x squared, 9x. I can factor out 9x. And I'm left with x plus 1 plus 4x plus 4. I can factor out a 4, and I'm left with x plus 1. In the denominator, 8x squared plus 8x. I can factor out 8x. Well, that's interesting. I just made a sigma. Who knew? Who knew I could do such a thing? Gamma, whatever that is. It's one of those Greek letters. I don't even remember now. I think that was a gamma. X plus 1. Right? If I factor an 8x, if I divide both of those terms by 8x, I'm left with x plus 1. And now I have a negative 7x minus 7. If I factor out that negative 7, I'm left with x plus 1. Well, I think you can see what's going to happen here. On the top, I have a common factor of x plus 1. And then I'm left with 9x plus 4. And on the bottom, I also have a common factor of x plus 1, but I'm left with 8x minus 7. So, what can I do? Well, now that I've factored everything, chop that off. X plus 1 over x plus 1 is 1. They cancel each other out. And I'm left with my final answer, which is 9x plus 4 over 8x minus 7, and isn't math wonderful? And there's my answer. I simplified everything that I could. I factored, I canceled out the common factors, and that's what was remaining. All right, two more quickly, two more, and then I'm going to be done with this lesson. This one is, we're almost there. Real quick, what if you have this? 2 plus x over x plus 2. All right, now, don't get fooled by the fact that these are not written the exact same way. Remember, addition is commutative. So, all I have to do is take one or the other. Let's take the numerator and switch the order and rewrite it as x plus 2 instead of 2 plus x. Well, now, they're the exact same, which means they cancel each other out, which means that's equal to 1. Simple, plain old 1. All right, now here's one that's similar, but not quite identical. 2 minus x over x minus 2. Now, subtraction is not commutative like addition is, so we can't just flip the top around and make it look the same. I can rewrite it in a different order as long as I keep the signs in the correct place. So the top I could rewrite as negative x plus 2. Notice that's the exact same thing as 2 minus x. The 2 is still positive, the x is still negative, over x minus 2. Now, comparing the numerator and denominator, what do we see? Well, we see that we have the exact same term except the signs are backwards. Luckily, we can fix that. What if we just factor out a negative 1 on the top? In other words, if we divide both the negative x and the 2 by negative 1, what does that leave us with? Well, it makes this a positive x and a negative 2. Right? Anytime you factor out a negative 1, you're just going to switch the signs. That's all that happens. Over, well, we didn't do anything to the denominator, so it's still x minus 2. And now what happens? Well, we've got x minus 2 over x minus 2. They cancel each other out, and all we're left with is negative 1. So instead of positive 1, like we got in the previous problem, we get negative 1. Okay, that should give you everything you need to complete the Lesson 6 assignment.